Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Silexica with Juan Eusse, who's going to talk today about getting software through an HLS flow. So Juan, in the early HLS tools, there was a conception that these things would do almost everything, that they would be able to synthesize software. Reality is that's not the case though, right?
No. In reality, you have software that's produced by general purpose programmers to run on a processor, but their focus, the processors have a high abstraction level, and the architecture is really hidden by the compiler. Whereas the FPGA is actual hardware, and you need to be aware of the details of the hardware. So general software uses concepts like dynamic memory allocation. That doesn't really apply because you cannot really create more memory on an FPGA. Your resources are already constrained by the chip.
And memory in hardware is a completely different concept than it is in software too, right?
Yes. I mean, in software, you have your different levels of memory. You have the memory on chip, you have caches, you have like the registers on the processor, and then you have bigger storage elements like the disk, for example. Whereas in the FPGA, you have block RAMs, maybe you have in the new ones, you have ultra RAMs, and they're fixed, so you cannot really use external memory. Or you can connect to external memory, but the latency is way too big, so you will lose the performance you earn through hardware acceleration, you will lose by using external memory, so you need to be careful.
So why don't you draw this out for us?
Yes, sure.
So Juan, what are we looking at here?
Yeah, so this is a very basic example of when code that's written by a software programmer is not synthesizable. In this example, you have your main function here that's executing some code that we're not depicting here, and it's calling some function foo, which has two input arguments and one output argument. Now, it turns out that foo really is getting two integer pointers as inputs and one integer pointer as an output. And then it's doing a for loop over some samples, and then writing on a variable c. So the output is the result. It's accumulating over the multiplication of two outputs.
So where do people typically go wrong with this?
Yeah, exactly. So you see, if you pass a pointer as the argument of the function, an HLS tool will not be able to realize that this is indeed a memory or a local array or something like this. And furthermore, it cannot really know the size of the array A. So it cannot know that A is of size sampled. So it doesn't know what's the size of the memory that it needs to synthesize in hardware.
So this is where a lot of your performance and actually your power as well will come from, right? You'll be able to optimize using this kind of coding. I
mean, the whole approach would be that you need to define the size of your arrays in order to have efficient hardware. So you cannot really say, okay, my A can be from 10 positions to 1,000 positions, because you will be wasting memory. So a good designer will go analyze the application and determine the size of the arrays, which is in this simple case, it's samples. So a good HLS coder will take this code and then translate it into something like this. So the function argument will be of fixed size, and then the HLS tool knows that it needs to synthesize an array A of 32-bit positions of size samples.
So this is a good intro. It gets a lot more complicated from here though, right?
Yes, exactly. So in let's say code in the wild, you will have functions like this, but in which you don't have arrays, but you have structures, and they will be passed by pointer through the call hierarchy of the functions, for example. Or you have data that's allocated dynamically because this code was written to run on a processor, which has a heap management system. In an FPGA, you don't have this, so you would have to go and replace all your dynamic memory allocations in your code.
So how does this play out in the real world? Give us a real world example.
So for example, you could have a chip that's going to do some computer vision algorithms, and you need to connect it to different cameras, which will have different formats. Now, what a designer would do is make this code and fix the arrays, so fix the different formats that the algorithm needs to work on, introduce or adapt the functionality of the chip via C code, which is still synthesizable because it knows the size of the arrays it's going to be processing. And then the implementation that the HLS tool will produce for this chip will already take this into account.
What happens in something like an AI chip? How does it change there?
AI is a bit more complicated because it's a rapidly changing market. I mean, you have the network architectures are not fixed. Also, the precision of the networks are not fixed. You can have networks working on single precision floating point, half precision floating point, integers, and binaries. So you would have to have an extra layer or an extra tool that will convert the network to whatever you want to implement and then put it through the HLS.
And this is one of the reasons that HLS is becoming so popular too, right? Because you do have things that are changing all the time, like algorithms, and they're not necessarily fixed the way you would have something that classic von Neumann architecture, for example, where that's been around for 20, 30 years.
Yeah, I mean, and that's the advantage of the FPGAs, right? HLS is a way to democratizing the use of FPGAs, which are efficient because they're hardware and they're flexible because they can be reprogrammed. Now, the main challenge of programming FPGAs is that you still need hardware expertise. But by raising a bit the level of abstraction in which you describe the circuits, then this helps designers adapt their algorithms in a more efficient way.
Is the expertise pertinent only to hardware or software, or is it domain expertise as well in something like automotive?
I mean, this is embedded. You need the domain expertise to be able to create an efficient implementation for an application.
And so the end application is going to be critical in all of these, in addition to your knowledge of hardware and software.
Yeah, of course, yes. You need to analyze the algorithm in order to produce an efficient hardware implementation, but then there is HLS and there are tools that help you at least get to the hardware implementation faster.
So where do you see HLS evolving? What can you do now that you couldn't do maybe a year ago, and what's the long-term strategy here of what you see maybe a couple years down the road?
I mean, for me, HLS is the assembly compiler for hardware. I mean, at the beginning, people used to keep coding in assembler because the compilers were not that good. Now, no one dares to use assembly unless it's for a highly specialized purpose. A year or 2 years ago, you wouldn't see big designs being created in HLS, but we have seen, or I have seen in the literature, that now neural network accelerators, video codecs, 3D imaging processing is being created in HLS. So all these algorithms that are highly changing are already being implemented using HLS tools because of the efficiency that the tools and the abstraction level give designers and the adaptability that these bring.
Juan Eusse, thanks for a great explanation.
Thank you for the interview.